is up here. I'm not sure it's charging or not. Yeah, I think it's charging. I don't know. It looks like it's stop, but it's okay.
This first part is really like regular ordinary, so it's kind of boring part. So this actually is equal to multiply from 1 to size n key x in unity. And now we are going to calculate this part for multinomial distribution. That part is equal to 1 n mu x times 1 minus mu 1 minus x. So this is the probability. This is probability of d given theta. Well, this theta is the general parameter. Here it stands for mu. We are going to compute the theta which gives the highest probability of this form. So this is because this is kind of complex to compute, which is all multiplies. So we usually take the log form of this distribution, which is log likelihood of theta is equal to log given theta, which is if we plug the log in here, so we have this multiplication becomes the summation, and this x comes into here, mu. And these times become plus. Log form of this formula.
That one is it. Log of the theta.
This one?
Yeah.
Oh, this is like likelihood L.
Oh,
so
okay.
this is
defined,
defined like this. Because the law is growing like this.
Yeah.
So if we maximize this, it's equivalent of maximize this. So if we want to maximize this function, and this is the unconstrained optimization with a single variable. So we just take the derivative of mu and set to 0, and which is equal to 1. If we take derivative of this function of mu and set to 0, so we have like this, mu becomes the derivative for mu becomes this form, and plus 1 minus x, 1 minus mu over 1, set that to 0. And we just expand this. this a bit by times 1 minus by normalizing this one. So this is too boring. Is it? Okay. If we move this term to this right side, so we have that equals to u is equal to minus 1 over n of xi. So this is the sample mean of this axis. This is a critical point of this maximum likelihood. So one problem of this, the benefits of this method is that it's kind of intuitive, and you have theta that maximizes this likelihood, then you get the parameter. But the problem of this method is it's first of all it's point estimate. So it only gives you a single theta. And this doesn't even give you a distribution of how confident it is for this estimation. And another thing is this apparently is overfitting, because a classical example is going to be if you are tossing coins. If you toss that 3 times, then you got 3 heads. And if you do a maximum likelihood estimation of this mu, you are going to get the points are always going to be had, which is obviously wrong. So a fix of I can say it's pretty boring, so I'm going to skip the derivation for categorical distribution and imaginary. And the fix of this method is going to be maximum posterior. And maximum posterior is taking a different form. It is equal to max theta, but this time instead of data given theta, this time it's theta given data. So if you have observed this data, what's the probability of theta? This, if you use the base rule, this is theta given data is going to be p data given theta times p theta and over pd. Here we can consider this has nothing to do with theta, so here we can consider this as a constant. If you want to maximize this value, well, this is proportional to d given theta, theta. And if you remember, this is the likelihood function. This term is likelihood, and this is the probability of theta. So, if you go back to the example of closing points, you can see if we estimate the points is always going to be had. This is basically not very possible on all points we have seen. So this is.
What do you mean probability of data?
Probability of data is the probability of you having this, observing this data. So here we are not going to use it anyway. So to maximize this, we have to maximize these two terms combined. And here we have a term for this called this is called prior of the parameters. It turns out to be you can choose many priors for this maximum posterior estimation, but there are some of them are conjugate to the likelihood function. By conjugate here we mean, well, if this term is conjugate to this term, then the posterior distribution of the posterior distribution is going to be in the same form of this prior distribution. This is a bit abstract. So let's still start with an example. So say we still have the coin estimation problem. Actually, categorical problem distribution is a bit more interesting to see. But to get an idea, we start from the binomial distribution. If you still think it's too boring, I might just cut something else. And remember this term is, this time we still have a bunch of data. P, D given theta is equal to P x1 given theta, P x2 given theta, P x given theta, which is equal to still times all the data we have. In the Bernoulli distribution case, we have this form. turns out the conjugate prior for this Bernoulli distribution is called a beta distribution. The beta distribution is defined as X parameterized by we call it A and B. This distribution is equal to the beta function of A and B over 1 over this, and let's leave it. I know that this stuff, when you look at it, it's kind of boring, but when you use it, it's kind of fun. I know it's kind of boring now. Which one? Oh, this is the X. Bernoulli distribution, this X means the outcome. You can see if, if this is a Bernoulli distribution, there's only 1 and 0 as outcome.
Yeah.
So if X is 1, then this term becomes 0. So this big term becomes 1. So this is the probability of like hat. This is just a fancy form of writing this if else if you write code. It's not very different.
And what is the beta?
Beta distribution?
Yeah.
Beta distribution is it's a conjugate prior of the Bernoulli distribution. So the conjugate prior basically means if they have it's a distribution over distribution. So yeah, I'm going to explain this later. Yeah. So you can see this is a distribution over mu parameterized by A and B. So here we are trying to
What's the shape of this distribution?
yeah, that's a good question. So we can start from plugging some value of A and B. So if we plug in 1 and 1, so this is going to be only this term. So because this term becomes 0 and this becomes 1. This becomes 0 and this becomes 1. In case of A and B are both equal to 1. So in that case,
Sorry, what is B?
B?
Yeah.
Oh, B is a parameter from this B.
No, yeah.
Which one?
B or B?
Capital.
B.
Oh, this B.
Yeah.
This is called beta function.
Oh.
This has, you can consider this as a normalizing constant.
Oh.
Because this two term, when divided by this, needs to be equal to, well, integral or summation need to be equal to 1. So you can just consider this as the normalizing factor. And the distribution of this mu when A and B equals to 1 is going to be something like this. Because this is simply like a line. Yeah, this is probability distribution. This is value.
This one is probability distribution. This one is mu.
You see, mu. Yeah, this mu is between 0 and 1 because
And this one is B.
yeah, this is how likely it's going to be in this value. So it's like a constant. And if you have a, like for example, if you have a large A, for example 5, and smaller B, and from this distribution you see something like like this. See? So if you have like these two are equal, you will have something like this. So it's shifting the
Which one shifts A or B?
what is that?
A shift is shifting or B?
I think so. I think so. These two. And now we are going to have now we are going to compute this value. So if we plug in this part and this distribution, we are going to have like this summation.
What's the advantage of using beta?
What's that?
What's the advantage of using beta?
Oh, this one. Because sometimes we can, from the data, you can estimate, you can come up with the value of parameter, which is really rare. Just like a tossing coin example. You can't always get heads, even if the first three observation is our heads. So the parameter itself is pretty rare. So here we just put a control over that kind of parameter. If it's too rare, we're not going to pick it up. I think Sam is pretty boring about this.
No, it's okay.
Okay.
Is that problem with BA, capital BA, A and B in the bottom?
Oh, that's just normalization factor.
It's some function or it's
Now you can think of a constant because
But
for each AB is a constant.
what's the effect of AB on this constant?
AB is just bounded. AB is just bounded in the sense that mu is the variable. So we are considering distribution of mu. So BAB is just a normalization factor. But of course, if you have different AB, then your normalization factor is
If A and B both of them are more than one,
More than one.
yeah, what does it mean?
It's finally we are going to expand this A and B as a pseudo count of the tossing coins, but we are not reaching that stage. We are going to,
Just for the tail, not for the tail, the number.
if we jump ahead, this A and B in context of tossing coins can be considered as, well, before I toss my coins, I know in my life I never observed any coins can only have one result. So I kind of believe deeply A and B should be kind of like 1 million, 1 million. Because every single coin I observe have this like even faces. So I'm confident. So I put like 1 million, 1 million over here. So which means I think the parameter is going to be 0.5. Mu is going to be 0.5. So then if I toss 3 times of coins, I get 3 heads. I think it's okay. It's just a random event. I don't think it's going to be head all the time. Because I've observed enough like even times of heads and tails in my life. So I don't think that these 3 really means something.
And another question, for the coin example, what's the mean?
For coin, what's the mu? Oh, this mu is the probability of coming up with head or 1. If you define 1 as head.
What's the probability of the
Yeah, because for the Bernoulli distribution, because there are only 2 outcomes, you only need to specify probability for 1 outcome. Then 1 minus the probability is going to be the probability of another outcome.
How can you find the capital B function for the coin example?
This B,
Yeah.
I think this B has a fixed form of some multiply of some gamma function, which I don't really go into because I don't need this to compute the distribution. Here I usually just consider this as a constant because many distribution you have this nice form here, it's kind of interpretable nice form over here, but you have to integrate this to one to call it a distribution. So this function, I just consider this as a normalizing factor. And if we keep like working on this, we will have times this distribution. Now I just call it constant C for now, because we don't need this term actually in the computation. And I can even remove it, but it's not really right. Maybe I should. C is this term.
Then do you use the better distribution for P of theta?
Yes, yes, yes. Because this is prior, like what I think before I do the experiment.
And for example, in the coin, do you use a big number and B a big number? Because you have some.
Yeah, that's depends on your belief. If you deeply think this is yes, right, then I choose a big number. If I think, well, possibly yes, I will just choose a small number. I don't really believe it, but I think this is the case. And finally, we are going to explain how your number of observation will weight between the maximum likelihood and the prior.
Why you add the beta distribution at the end of that?
Oh, this one?
Yeah.
Because here we are going to use the maximum MAP as the estimator of theta. And MAP is proportional to likelihood times P theta according to this rule. So here, if we are going to compute the, right now we are computing.
Okay, P theta is that? Just assume that the theta should be as beta.
Yeah, yeah. And again, we are going to, let's see. Again, we are going to take a log likelihood of this function. So we are having summation x from u and plus 1 minus x 1 minus u. Plus b minus 1 this is again a optimization problem with no constraint and single variable. This is the simplest form you can get for optimization right now. And you are going to take the derivative of mu and set to 0.
You want to take that this thing, right? So that you need to, you have the whole thing is the same from the sum over x and then like the sum over a minus 1. And then the solution to reduce like
before doing this, I just simplified this expansion is too long. And since the x is going to be only 0 or 1, so if we take a multiplication of this term, this is basically this term is equal to the number of x. Because, well, like 1, 1, 1, 1, 0, 0, 0, or 1, 0, 0, 0, 1, 1. You are going to only, the number of ones and 0 will come, but not the order doesn't matter. So here we just simplify.
I think it's not 1 minus x, it should be n minus x, right?
Which one? 1 minus 6?
1 minus mu, 1 minus x to the power is to the power n minus x. Because you flip x times and then you have like x times head and then n minus 6 times like tails, right? So instead should be like 1 minus mu to the n minus x or n minus x.
I'm going to write that.
No, I mean the equation before, like the third line on the
Third line?
Yeah. Do you want 1 minus x or n minus x?
Oh, here is still the x, here is still like 0, 1. This is just the original.
X is your data, right?
Yes. 0, as a 0, 1.
Oh, okay, x is 0 or 1.
Okay. This is
Okay.
original.
Okay.
So here we are going to do what Sam was talking about. So we are assuming like number of ones, number of x's is, well, any number is fine. We just call it like m. And this is equal, and times the probability of like tails, which is n minus m. Is it what?
Yeah.
Okay. So then we don't have this like multiplication, property multiplication. And then we can move this form here. And now we are going to this is original form. Now we are going to take the log like we are going to take a log of this form, because multiplication is always more difficult than the summation for computation. So if you take log form of this p, we are going to have m plus minus m times log 1 minus mu, and minus mu take derivative is going to be a minus 1, so this becomes like minus some. And here we still plus a minus 1 times mu plus, it's still going to be minus b minus 1. Then if I take the, again we are going to find the maximum of this function. So single variable, unconstrained optimization. So we just take the derivative to mu. We are going to get, and set to 0 of course. 0 is equal to m times 1 mu. minus 2. Wow,
Yeah, maybe you can.
this
No, this is
when they convert it, they're going to become minus 9.
okay. You apply the derivative and change it to minus.
Yes, I'm going to write it here. Here I'm just taking the log. Yeah, here I'm just taking the log. Okay.
Yes, yes.
Okay, so I'm going to now take derivative, and this becomes minus so let's merge the form. So we have a mu m plus a times minus 1 and the minus 1 over mu n minus m plus b minus 1. This is still 0. So we are still trying to get the mu out of this form. Looking at someone else deriving equations, I know it's boring.
Actually, I guess you don't even need that. I mean, why don't you group the terms together first? It's just like mu to the a plus 1 minus mu to b, for example. Then you should get result something like mu should optimize at like a over a plus b, something like. I mean, just like a equal to m plus mu a minus 1 and big b. I mean, yeah. For example, c equal to m plus a minus 1 and b equal to m minus m plus b minus 1.
How do you do it?
Let me do it. 2 seconds.
Otherwise, it's boring.
Reduce
Yeah, we should do it together.
Why don't you put that together? I mean, what you're interested in,
Oh, yeah,
is something like
Yeah, you're right. Yeah.
Well, like, you will see that
So, yeah, I think you're right. And here C is equal to, C is for U. C is equal to M minus, plus D minus 1. And D here is equal to
A. M is equal to, C equal to M plus A minus 1.
Oh yeah. Can't even read my writing. D is like n minus m is m plus b minus 1. So and same plus d is actually n plus a plus b minus 2. And then so here, as you asked before, what's A and B? So here we can see, we can consider A and B as a pseudo count before we actually see the data. And here is the total number, total number of coins we observed before. So after in this particular experiment, we see n of them because the data is like side of size n. But before we even see this, we have observed this number, total number of coins, like tossing coins before.
Yeah, A plus B is the before observation.
Yeah, before observation.
Now, N is something like the number of the observation. Now, just observe. Yeah.
That's
Both
n,
of them. Yeah,
That's
both of them count.
And this is in the experiment we observed m times of heads. This is before the before the experiment we see like a times of heads. So this has a very natural interpretation. And it turns out that this form is a convex combination of the prior and the maximum likelihood of the current data. And I don't remember if I can write that out.
What did we exactly?
Combination? Or
Say that again when you said it's
I mean, this result is actually a convex combination of prior your belief before experiment and the data you observe. I can.
How do you define convex combination?
Well, convex combination is kind of there's x, there's y. If you add them together with a plus coefficient, say there's coefficient alpha, this plus 1 minus alpha. This is a convex combination of x and y. And it turns out this result is a convex combination of maximum likelihood result and the prior. Let's see if I can write it out. For the maximum likelihood, the result is the number of heads over the total number of observation. For the prior, the result I think is going to be something like over this. I wrote that deposition there. Just in case I can't. I don't remember. Yeah, I just explained this form. So this is the number of, this is the prior, A and B. This is here. This is M here, and this is M. I'll write this way. So these two coefficients, if you see them, they actually add up to 1. So which they add up to 1. So the meaning of this form is like this is number of observation. So given a prior A and B, the parameter of prior A and B, if you have very few observation n, then this coefficient is going to be like 0. This coefficient. So your estimation of from the data using maximum likelihood is not going to count, since this coefficient is like 0. But if you have a lot of observations, this coefficient is going to be 0, but this is going to be 1, almost going to be 1. So which means if I have a lot of observations, my prior doesn't really count. So if I have a coin, I try that 1 million times, and it shows a consistent result. So I can safely estimate my theta from the data I have now. I don't need to use any prior. And this is the interpretation of the MAP. It really depends on which value you put here and how many observations you make from your experiment. So this is a very nice form.
Okay, yeah. I got lost. The connection between this one and this one. Oh, just go there.
Oh yeah. This result.
I'll just convert this one to
Yes.
Okay.
Yes. They're the same form, but variable is probably different.
Yeah.
I don't know if I should go through more derivation because it seems very boring.
Oh, I don't know. I think it's good. I don't see any good derivation yet. Honestly, we do okay.
But I think
Okay, it's okay. Yeah.
Are you sure?
Yeah.
I don't want to make you sleep.
No. You just need to point out the key steps, but not start doing simple derivative, something like that. You just spend too much time on doing the derivative, but that you can skip. But like the derivation should be like have the key steps pointed out. That will be pretty quick actually. It won't take that long of time.
I thought about bringing a note.
Yeah.
You should actually.
Yeah, but I thought it's kind of practice to me also. Sometimes I pay much attention in derivation because I want to make it right. So.
Yeah. Hopefully next time.
But I honestly, I'm not impressed with the so-called complex combination because you have 2 points on 1D space. How can you not a linear combination of 2 points? Unless you have a 2-dimensional. Unless you have 2D things, it won't be complex combination of vectors, right? Basically, both of them is 1D. You have two points here, and you're talking 1 point with this here.
I think it's
I know, but I think it's not very impressive. Not very impressive, the things that pointed out. Pointed out where? Like, who pointed out this? Like,
I read
from the textbook?
Yeah.
From someone's textbook?
I don't remember where. I think it's just kind of.
I mean, it's not silly because if you think of like a high dimensional, so that things whether like a line on that point line is then it's like, but you are basically like 2 points or 2 points. It's not actually you have to.
Yeah, but maybe it's
Yeah,
obvious.
yeah, it doesn't, yeah.
So I heard of this.
But anyway, this is maybe not good for account, but this kind of stuff is good for proposals.
Really?
Yeah, it's kind of like. Yeah, I'm not good at that. That's the problem.
there's a, but still the MAP, still the MAP is still a point estimation. So anyway, you have one single value come out of this calculation. So, but there are chances that the point estimation.
Excuse me. Before continuing, is there any route to find the P of theta? Because you, for example, select a distribution for P of theta to make the, for example, calculation easy.
Yeah.
How you find
How there? I think the simple answer is there is a table. There is a distribution mapped to a
but I think
content prior.
but I think for finding the good distribution for the prior, you need to know the final result, and based on that, you find the distribution to match to your prior to reach that. Is there any way to, for example, any distribution or any technique that you can use for the prior?
One clue to solve this problem is it turns out not most, I think all of the member distributions in exponential family, all of them have computed priors. I think from if you transform a distribution to an exponential family form, I think from there you can get some clue to find like you said, find the prior. I think there's some way to do it. Okay, so I almost forgot. I prepared the exponential family. Almost forgot that. Okay, so let's maybe take a small digression to the exponential family. So we'll go back to basic method after, if we have time. So I think Sam last time in information theory or some class derived the exponential family is like some from energy perspective you have to minimize maximum entropy. Yeah. So it turns out there for lot of distributions such as Bernoulli, Gaussian, and you name it, lot of distributions are from the exponential family. But the exponential family has a common feature that the distribution can be written in a form like Px. Px parameterized by a natural parameter eta is equal to like g of eta times. This is like when I first saw it, doesn't make sense at all. It turns out to be useful. And fx and exponent of eta is inner product of sufficient statistics of beta x. And again, this function is a normalizing constant. If we integrate over x on this term, it's not going to be equal 0 in some time. And then you need this normalizing factor to make it 1, make it probability. And this S is sufficient statistics, which basically means you don't need to keep the x to do any calculation. You only need to extract some feature of x, and then you can do whatever you want. And
This
f, I'm not sure. I can derive x from a distribution, but I don't know what does that mean, f. We can derive from any distribution like Bernoulli and get f, but I don't know what's f exactly. what's the point of having f?
Then
I guess it makes the distribution
harder.
harder. Let's see an example of Bernoulli distribution in terms of exponential family, and then we are going to go to the deriving maximum likelihood for exponential family. And if you have time, you can go to the generalized linear model from this exponential family. And so we have a Bernoulli distribution. You can see the if we u is equal to x mu times 1. This is the mu x 1 minus mu 1 minus x. This is the Bernoulli distribution. So you can see if we want to transform this distribution to exponential family, we have a exponent here. So to get this exponent out of this, we can do a simple trick. We can take the exponent and then of the whole thing. X. We can do this. And then this is equal to dx x log mu plus 1 minus x log 1 minus mu. This is exponent. And yeah, we can expand this further. This is equal to x log mu plus log 1 minus mu minus x log 1 minus mu. And since in this form we only need this eta and the x, some form of x. So any terms that not involve this, we can move it out of exponent. So this is equal to dxp x minus log mu, and I think it's minus x log 1 minus mu. And then this is because this is a plus, you can just times dxp 1 minus mu. This is their equivalent. So here,
I think without exponential.
what's that?
The next exponential.
Oh yeah. There's a log.
Yeah.
Yeah, right.
Yeah.
We can cancel exponent and log and we get 1 minus mu here. It's a good catch. And then if we take the x out of the this term, and we can get this dxp x times log mu over 1 minus mu, and times what you said 1 minus mu. And if we contrast this form to this form, then we have x is here, and eta is here. So we have a eta equals to log mu 1 minus mu. This is eta, and sx is just equals to x. So, and right now we have this part, but this part what's up? And here we have a mu and eta. Yeah, actually this part. We have mu and eta. So if this function is take eta as parameter, we need to somehow turn the function into g beta. So we just we go, yeah. So from here we start again, mu minus mu. So we take exponent from both sides, exp beta is equal to mu 1 minus mu. So we multiply this to this side. So exp beta minus mu exp beta is equal to mu. Yeah. So we move this to this side, mu exp beta. And now we get exp beta will 1 plus exp beta is equal to mu. So we simplify this a bit by dividing both part with the exponential eta. Then we finally get mu is equal to 1 plus exp minus eta. We get this form. So does this form look familiar to you? Do you think this does it look familiar? This form. This is sigmoid function, which if you do a logistic regression, it's a very elementary classification algorithm. Logistic regression. You actually use this function as a training, as your model. The only difference is if you have this eta, if it's equal to linear combination of your input data, then this is exactly as a logistic regression. And actually, we just gone through the generalized linear model, and the assumption here we make is the natural parameter eta is a linear combination of x or functions of x. This is the assumption of the generalized linear model. So the implication is that because like Poisson distribution, Gaussian distribution, Bernoulli, and multinomial category distribution, well, a lot of the distribution we use in daily use can be written in this form. If it can be written in this form, you can always get the represent your parameter of the distribution with the natural parameter eta. And with the assumption of eta is the linear combination of x or functions of x, you can basically train any exponential family distributions with this method. So, for example, if you are an owner of a grocery store, you want to predict, given the weather and festival or whatever, given all these features, you want to predict what's the probability of the next period of time, what's the probability of there's customer coming in, which can be modeled by a Poisson distribution. And because Poisson distribution is a member of exponential family, we can actually go through exactly the same step and derive the model for this problem. I think this is, for me, it's pretty cool because you can model a lot of things with the exponential family, and with this simple assumption, you can actually model these things and get an algorithm for prediction. So I think this is kind of really powerful stuff.
Okay.
This is for diagram of generalized linear model. Let's skip that. I don't know, is it too late?
Yeah, I guess maybe you can use the Friday also. Yeah.
Friday or next Monday?
So who is in next Monday actually?